Have you ever paused in the glare of your phone screen and wondered how, in an era of instantaneous communication, so many voices still remain unheard? We live in the most connected moment in human history. Satellites orbit us, cables traverse oceans, data pulses through the ether, and yet isolation, silence, and longing persist at epidemic levels. It is a paradox. Ever more luminous webs of technology, and yet ever darker rooms of inner disconnection. We measure progress by bandwidth and compute speed, but we struggle to measure meaning. We launch probes to the far ends of the solar system, yet many of us can't land in the present moment of our own lives. This paradox is not an accident. It is the shadow that follows every leap of knowledge. But it is also the reason why we look upward and outward to see ourselves more clearly. And now, NASA is obsessing over Titan, Saturn's largest moon, shrouded in orange haze, with seas of liquid hydrocarbons, rivers that flow under alien skies, and a surface colder than liquid nitrogen. At first glance, Titan seems to be the opposite of Earth. Yet it may turn out to be one of the most compelling mirrors we have ever held up to ourselves. Why is NASA so obsessed with Titan's oceans now? Because in those alien seas lies not just the possibility of life, but a message about the conditions, the fragility, and the trajectory of every watery world, including our own. Titan is a future looking back at us asking, what does it take for oceans to endure, for life to persist, and for curiosity to survive? Let me take you on a journey not just through the distance between Earth and Titan, but through the distance between knowledge and wonder, between history and destiny, between human fragility and cosmic responsibility. Picture this: Saturn, that beautiful ring giant spinning far from the sun day. Around it circles Titan, large enough to host an atmosphere, heavy enough to hold cryogenic seas, mysterious enough to confound our best instruments. Its sky is orange from smog-like haze of methane and nitrogen. On its surface, rivers of methane carve channels and lakes of ethane and methane pool in basins. Beneath those hydrocarbon seas, hidden beneath crusts of ice, scientists speculate there might lie a subsurface ocean, salty, watery, possibly warm. Imagine that contrast. Seas of methane above, seas of water below. It's like two worlds in one moon. A chemical stratification that challenges our Earth-centric intuitions about what ocean means. When we hear ocean, we imagine waves of liquid water, sunlight dancing on surfaces, life teeming beneath. On Titan, an ocean is dark, frigid, suffused with chemicals we regard as alien. Yet the physics is the same. Diffusion, convection, energy gradients, solutes and sediments. Titan's oceans speak a language that our geochemistry understands, even if our biology is still learning the dialect. Now, let's rewind in time to the great voyages of human curiosity. In the 17th century, when Galileo turned his telescope to Jupiter's moons, he wasn't just discovering new objects, he was shaking the cosmic mirror. He showed Earth was not central, that satellites could orbit other planets, that the heavens were dynamic and surprise-laden. Every time we point a new instrument at the sky, we risk becoming uncentered. It is a dangerous but necessary humility. In 1977, the twin Voyager probes left Earth carrying a golden record, our message, in a bottle cast into the interstellar sea. They carried images of whales, greetings in many languages, and the song of Earth. But they also carried what we were: curious, hopeful, fallible. Our scientific ambition is not just to go, it is to remember who we are. Fast forward to Cassini, launched in 1997, which spent over a decade exploring Saturn and its moons. It flew through Saturn's rings, spiraled around Titan hundreds of times, and revealed things we never expected. Active plumes on Enceladus, volatile chemistry on Titan, mysterious lakes, seasonal changes, and glimmers of energy in dark places. Cassini taught us that the solar system is not a dead clockwork. It is alive with processes, surprising dynamics, and unsolved mysteries. Among its most striking revelations, Titan isn't static. Its surface shifts, its lakes change with seasons, perhaps waves ripple under certain conditions. There are hints of geological activity, of currents, of something stirring under the ice. These findings force us to revise how we think about habitable zones. Titan orbits far outside the classic Goldilocks zone for liquid water under sunlight, yet it may harbor water in its guts. Habitability is not a fixed box, but a gradient of possibility. So here we are in the second quarter of the 21st century, and NASA, along with ESA, JAXA, and other agencies, is turning its gaze back to Titan with renewed official missions. Dragonfly rotorcraft lander, proposals for subsurface floaters, remote sensing strategies, and increasingly ambitious instruments. The obsession is not whimsical, it is urgent. Because Titan's story is not merely about alien seas, it's about the future of Earth's seas. Let me explain why. We often think of Earth's oceans as robust, deep, vast, resilient. But oceans are dynamic. They have tipping points. They respond to heat, they respond to carbon, to acidification, to overharvest. They shape climate, sequester carbon, regulate weather, nourish ecosystems. They are the planetary circulatory system. Now imagine a moon like Titan with surface lakes and subsurface seas. If those seas are real, they might be vulnerable in ways we often discount. If energy flows in or out of the system change, like from tidal heating or radiogenic heat, the balance of chemical gradients can shift, currents turn, and conditions for life can vanish or emerge. Titan may simulate, in extreme form, processes that are subtle on Earth, but vital to maintain balance. If we learn how Titan's ocean interacts with its crust, how methane cycles through atmosphere and surface, how energy transports beneath, we may gain insights into Earth's ocean resilience, how long stability can last, what thresholds exist beyond recovery, and how seemingly inert systems can suddenly shift state. Titan is thus a laboratory, scaled differently, cool to extremes, far from sunlight, but telling us something about sustainability. It is the distant echo of Earth's potential futures. Let me draw a metaphor. Imagine Earth is a star burning with life, Titan a planet cooling toward quiet, not an end, but a slower rhythm. If we listen, Titan is whispering to us, what becomes of an ocean when its heat source wanes? It asks, can complexity endure in the dark? In that whisper lies a philosophical knot. Life is a defiance of entropy. Life draws energy from gradients, flows from hot to cold, from rich to poor, from high potential to low, to build, to grow, to reproduce. When gradients flatten, when the difference between warm and cold, between nutrient-rich and barren, becomes too small life struggles. Titan seas may be close to that limit, in an almost thermodynamic equilibrium compared to Earth's active systems. We are not so different. Our society draws energy from gradients of resource access, of innovation, of education, of justice. If those gradients flatten, if inequality stiffens, if opportunity stagnates, if information becomes inert, human flourishing also chokes. Titan is a distant, frigid mirror of what a world might look like when energy gradients collapse. That is why NASA's obsession matters. It is not escapism, it is humility. We send machines to Titan not because we plan to live there, though someday we may, but because we need to see the Arctic mirror of our own planet's tipping points, our own moral gradients, our own threshold of resilience. Titan's landscape is not carved by water ice, but by methane. Rain rivers erode, lakes evaporate, dunes shift. The materials differ, but the processes are analogous. Fluid dynamics, sediment transport, cryovolcanism, interaction of atmosphere and surface. One of the biggest puzzles is how the methane cycle replenishes itself, because ultraviolet light should break down methane faster than it can be replenished. There must be hidden sources, reservoirs, or subsurface processes feeding it. That raises a broader pattern. Unsurfaced hidden subsystems often sustain what seems visible and stable. On Earth, those hidden subsystems are our aquifers, soil microbes, deep ocean currents, carbon sinks, ecological networks. They are the foundations of life we barely see yet. If they fail, the system fractures. When NASA looks for methane replenishment on Titan, it is seeking those hidden supports. When we examine deforestation, groundwater depletion, biodiversity collapse on Earth, we are doing the same exercise, diagnosing the unseen scaffolding that holds life up. That link between deep unseen systems and surface stability is a cosmic metaphor with moral weight. It took courage for Cassini's team to send that probe into Titan's haze, into unknown risk. It takes courage to propose Dragonfly to dispatch a rotorcraft through an alien atmosphere with wind, methane, cold, and uncertainty. It will take still more courage to one day send subsurface probes, floats beneath the ice, or even human explorers. Curiosity is not safe. The universe is indifferent, sometimes harsh, often surprising. A ship can crash, instruments can fail, funds vanish, hypotheses collapse. But curiosity insists. It stakes a claim. I will know more tomorrow than I know today. And that insistence, repeated generation after generation, is how science grows, how civilizations rise. So NASA's obsession with Titan is not a luxury, it is a signal of bravery. It says, we will invest resources, span decades, accept risk, because knowledge is not a cost, but an inheritance. Now let me bring this back down, from space probes to your daily breath, from Titan's oceans to the ocean your body carries. Titan's fascination may seem remote, but everything that surprises us in space also surprises us in ourselves. When we learn how methane lakes shift on Titan, we sharpen our intuition about fluid dynamics, chemical balance, climate systems. When we design instruments to probe beneath Titan's crust, we improve technology for detecting subterranean water on Earth. When we retrain our imaginations to see life in dark, cold places, we become more generous toward fragile life in our own ecosystems. But perhaps the deeper lesson is moral, not technical. Because Titan seas press a question on us. What do we owe to a world when we are not its owners, but its stewards? What does it mean to visit, to observe, not to plunder or dominate? If NASA goes to Titan, it must do so ethically preserving, minimizing contamination, respecting what we don't yet understand. As we become cosmic explorers, we carry the responsibility to care. On Earth right now, 70% of our planet is ocean. Those seas sustain billions, fisheries, climate, oxygen, culture. They are threatened. Acidification, overfishing, warming, pollution. The more we understand alien oceans, the more we can appreciate the fragility and uniqueness of our own. Titan's distant lakes become a kind of poetic alarm, anomalies that deepen our gratitude for Earth's habitable water. So here's the compact I offer you. Curiosity is not escapism. Wonder is not distraction. They are the scaffolding upon which meaning is built. When you learn about Titan's lakes, let it humble you. When you hear that NASA will send a rotorcraft across a frigid sea, let it excite you. When you ponder the chemistry in that alien haze, let it remind you how much we still don't know and how beautiful that ignorance can be. Let it move you not toward cosmic distraction, but toward cosmic responsibility. Human history is a series of telescopic leaps. We first looked at the moon, then Mars, then the faint glow of distant galaxies. Each time we crossed new horizons, humanity expanded a little, not just outward in space, but inward in awareness. We discovered that Earth is small, fragile, precious. We discovered that life is tenacious. We discovered that matter, space, time, information, they all conspire to surprise us. In the same spirit, we now look to Titan. We don't go because we own the cosmos. We go because the cosmos in that haze and ice and liquid may hold pieces of the story of life, of stability, of balance. In that murky light, we see reflections of Earth's seas, our own moral gradients, and the risk of flattening our planet's life. So let us decide now, today, how we will carry forward this age of discovery. If we send a craft to land, it must carry humility. If we drill beneath the ice, it must carry caution. If we explore, it must be in partnership, not conquest. If we learn, It must transform how we tend our home, because Titan is more than a moon with seas. It is one of our most powerful teachers. It tells us water crafts worlds, boundaries hold stories, hidden currents sustain life, and small differences make entire systems flourish. When NASA sends drones across Titan's orange skies, when a rotor touches down on frozen dunes, when sensors float in cryogenic seas, those are not just feats of engineering, they are statements of faith. That knowledge matters, that life matters, that discovery is worth risk when guided by love. We live in a moment of planetary fragility and cosmic possibility. The same reason we look to Titan is the reason we must act for Earth. Let us be guardians, not conquerors. Let us be students, not masters. Let us remember that we are not apart from the universe. We are its way of noticing itself. So go on, look up. When you read the headlines, follow the news of Titan, watch the images roll in, let your wonder be a tether to responsibility. Because the moon with seas of methane is reminding us we are not the owners of our planet, just its stewards. And in the care we give today lies the legacy we leave among the stars. There's a particular kind of silence in space, the kind that isn't absence, but anticipation. It's the silence that existed just before Cassini dove into Saturn's atmosphere, sending its last whispers home. The silence before Apollo 11's static broke with the words, "The Eagle has landed." And soon, it will be the silence before the blades of a nuclear-powered drone slice through Titan's orange sky. NASA calls that drone Dragonfly, and for good reason, because it will not crawl or roll, it will leap. It will fly from dune to dune, crossing more ground in a day than some rovers have in years. It will be the first rotorcraft to explore another world. Dragonfly is no ordinary machine. It's an 8-rotor quadcopter, about the size of a small car, equipped with instruments to sniff the air, drill the soil, taste the chemistry of another world. Its mission: to search for the chemical precursors of life, to find out if Titan's icy hydrocarbon landscape once brewed the ingredients of biology, or if it still could. Launch is planned for the middle of this decade, arrival in the next. The flight will take nearly 8 years, an interplanetary migration of technology and intention. When it finally descends through Titan's haze, it will do so guided by algorithms, cameras, and human hope. It will hover above a world where the rain is methane, the lakes are liquid natural gas, and the sunlight is 100 times dimmer than Earth's. But why Titan? Why now? Because Titan is the only place in the solar system besides Earth where liquids flow freely across the surface. It has rivers, lakes, even seas, though they are made of methane and ethane instead of water. Its atmosphere is thick and nitrogen-rich, its pressure comparable to ours. In some ways, Titan is a colder echo of early Earth before oxygen, before oceans teemed with life. To study Titan is to time travel, to rewind the chemical story of our own origin. NASA's obsession is not just about curiosity, it's about continuity. The agency sees Titan as a link, a natural laboratory where chemistry may have rehearsed for biology. By exploring Titan, we're looking for the bridge between the inanimate and the animate, between matter and meaning. Imagine the view. Dragonfly drops through a golden haze so thick it turns daylight into twilight. Below, dunes ripple across a frozen plain, dark ridges made of organic sand. The sky glows amber. The temperature hovers around 290 degrees Fahrenheit. No sound but the whirring of blades. And yet, beneath that alien quiet lies motion, an entire moon breathing, cycling, changing. Methane rain may be falling somewhere far to the north, carving channels into the terrain. Beneath the crust, a buried ocean sloshes a global sea of salty water mixed with ammonia. Heat from Titan's core stirs it gently, just enough to keep it liquid after 4.5 billion years of cold. Every time Dragonfly lands, it will sample, measure, it will analyze the molecules in the air, searching for complex organics chains of carbon, hydrogen, nitrogen, and oxygen that might resemble the first recipes for life. It will drill into the ground, testing how far chemistry has gone in the absence of biology. We used to think life required warmth, sunlight, comfort. Titan laughs at that assumption. It asks, what if life could start not in light, but in shadow? What if existence is less about temperature and more about opportunity? To land on Titan requires faith in physics and in people. From 4 billion kilometers away, we must guide a fragile craft through an alien atmosphere, communicate through radio signals that take more than an hour to reach home. Every command must be right the first time. There is no joystick, no second chance. But perhaps that's the essence of exploration, the willingness to act without certainty. Science at its best is structured courage. We build equations and engines not because we're sure of success, but because curiosity leaves us no other option. Dragonfly's mission is funded by the same restless impulse that drove the Polynesians across the Pacific, the same impulse that sent Voyager past the heliopause. We are the only species we know of that can imagine a world and then physically go there. That capacity, the ability to turn imagination into propulsion, is humanity's most dangerous and most beautiful trait. When Cassini was launched in 1997, it carried a smaller probe named Huygens. In January 2005, Huygens parachuted through Titan's atmosphere, sending back images of drainage channels, river deltas, and smooth plains. It survived for only 72 minutes after landing, but that hour changed everything. It proved Titan wasn't a frozen wasteland. It was an active world with weather, erosion, and chemistry. It was a world worth returning to. Now, 2 decades later, we are returning not with parachutes, but with wings. Dragonfly is Cassini's grandchild, built from lessons learned, equipped with instruments a generation more advanced. Where Huygens touched down once, Dragonfly will travel hundreds of kilometers, sampling multiple sites. It will study how energy and chemistry dance together, how a world that should be dead manages to look so alive. NASA scientists chose Titan not because it is easy, but because it is right. It's the only moon with a dense atmosphere and a solid surface. The only environment where flight by rotor is possible. Gravity there is just 1/7 of Earth's, the air 4 times thicker. It's a pilot's dream and aviator's afterlife. Every space mission is really a mirror. When we stare into Titan's haze, we are seeing our own potential, our drive to know, to risk, to extend empathy to worlds that can never thank us. Dragonfly is a technological ambassador of humility. It reminds us that exploration is not conquest, it's conversation, because Titan doesn't need us. It has orbited Saturn for billions of years without complaint. The storms will come and go. The methane will still reign. We go not to fix it, but to listen, to understand how chemistry becomes context, how lifelessness becomes lesson, and in doing so, we become a little less lifeless ourselves. As strange as Titan is, its processes are echoes of our own. Its methane cycle mirrors Earth's water cycle: evaporation, condensation, precipitation, runoff. Its organic sands resemble the tarry hydrocarbons that fuel our economy. Its hidden ocean reminds us that what matters most is often invisible. If Titan's seas can survive under ice, then maybe Earth's can survive under pressure if we give them the respect they deserve. If Titan's chemistry can persist in such extremes, maybe resilience itself is the universe's most universal trait. NASA's obsession is not escapism, it's ecology on a cosmic scale. By studying Titan, we learn the boundaries of habitability. We learn where life could exist so that we can better protect where it does. Voyager's golden record carried greetings for beings we'll probably never meet. But Dragonfly carries something subtler: our questions. Every data packet it sends back will be an encoded version of the same question that has haunted humanity since firelight and cave walls. Are we alone? Even if the answer is no, even if Titan turns out to be sterile, it will still have taught us what it means to search. And that search, that persistence, is what defines us. Because in the grand narrative of the cosmos, knowledge is the only immortality that matters. So when Dragonfly lifts off from Earth, it will not be just a spacecraft. It will be the embodiment of a human sentence that has been unfolding for millennia. We looked up, we wondered, we went. The question that drives every mission beyond Earth can be reduced to 4 simple words. How does life begin? We've given that question 1,000 disguises, biosignatures, habitability, abiogenesis, but beneath the terminology, it's always the same act of curiosity. We're trying to reconstruct the first sentence the universe ever wrote about itself. Titan has become the laboratory for that mystery because, unlike most other worlds, it still preserves the conditions that might have existed before life took hold on Earth. It's as if nature left us a frozen time capsule orbiting Saturn. Its chemistry paused midway between chaos and biology. On Titan, sunlight filters through an atmosphere rich in nitrogen and methane. When ultraviolet photons strike that mixture, they ignite a chain reaction, breaking molecules apart and recombining them into complex organics called tholins. These are tar-like substances, brownish, sticky, filled with carbon chains that would make an organic chemist's heart race. Pollens rain from Titan's sky like snow, coating dunes and plains with the raw materials of biochemistry. It's the same chemistry that, on early Earth, probably took place in the air, in shallow pools, or around volcanic vents. Here, the process has continued undisturbed for billions of years, untouched by oxygen or biology. To walk on Titan would be to stroll across the ingredients list of life before the recipe was ever tried. The irony is that Titan's surface is too cold for water to stay liquid. The temperature hovers around 94 Kelvin. But beneath that frozen crust, gravity measurements suggest a vast global ocean of liquid water mixed with ammonia, a natural antifreeze. That hidden ocean may provide the solvent that chemistry needs to take its next step. Water is not just a medium, it's a matchmaker. It allows molecules to meet, interact, and sometimes, if the conditions are right, to organize into something that resists entropy just long enough to call itself alive. Astrobiologists often say that life as we know it needs 3 things: a solvent, a source of energy, and complex chemistry. Titan checks all 3 boxes just in an unfamiliar order. The solvent, liquid water under ice, perhaps even small pockets of ammonia water brine closer to the surface. The energy, tidal flexing from Saturn's gravity, cosmic rays penetrating the atmosphere, and chemical energy released when hydrocarbons react with oxygen-bearing molecules from comet dust. The chemistry, a soup of organics, methane, ethane, acetylene, hydrogen cyanide, and long-chain hydrocarbons circulating through cycles of rain and evaporation. To an Earth biochemist, that combination looks almost too good to be coincidence. It's as if Titan has been running the same prebiotic experiment for eons, waiting for us to check the results. Dragonfly will carry instruments with names that sound poetic in their precision. DRAMS, the Dragonfly mass spectrometer, will sniff the air and soil for amino acids and nucleobase analogs. DRAGON-S, the gamma ray and neutron spectrometer, will read the subsurface composition, and cameras will record the terrain in light so dim that each photon feels precious. If the craft finds patterns, ratios of isotopes, repeating chains of carbon and hydrogen that suggest polymerization, it would mean Titan's chemistry has crossed the first bridge toward biology, not life itself, but its handwriting. The discovery would echo across disciplines. It would tell chemists that complexity doesn't need warmth. It would tell philosophers that life may be a natural outcome of physics. And it would tell every child staring at the night sky that the distance between alive and not yet might be thinner than we ever imagined. Radar from Cassini has already hinted that Titan's icy crust is buoyant, flexing with Saturn's tides. Those ripples suggest a liquid layer roughly 100 kilometers below the surface. If Dragonfly's instruments detect certain isotopes of noble gases argon-40, krypton-84, they can estimate how much radiogenic heat seeps upward, how thick the crust really is, and whether that ocean could still be exchanging material with the surface. Why does that matter? Because the moment an internal ocean interacts with the surface, chemistry accelerates. It's like stirring a pot. After leaving it still for hours, the ingredients meet, the reactions multiply. If oxidants from above mix with reductants from below, Titan's ocean could become a vast electrochemical engine, capable of supporting metabolism-like processes even at cryogenic temperatures. That's not speculation, it's thermodynamics. And thermodynamics, as far as we can tell, is the universal grammar of life. Every new discovery on Titan reshapes how we think about habitability elsewhere. If life or even pre-life can exist in liquid methane, then our definition of the Goldilocks zone has to stretch far beyond the warm belt around a star. It means that worlds once dismissed as too cold, too dim, too strange might be nurseries of chemistry. It means the galaxy is not sparsely inhabited, but chemically exuberant. Already, telescopes have found exoplanets with methane, nitrogen, and water signatures, mini Titans orbiting other suns. Each one could host versions of the same chemistry, writing variations of the same molecular poem. When NASA obsesses over Titan, it isn't just chasing one moon's mystery, it's calibrating our cosmic expectations. It's teaching us how to recognize the fingerprints of life anywhere, not just in Earth's image. It's easy to dismiss this as remote curiosity, but think of what these discoveries imply. If life emerges whenever chemistry and energy have a chance to dance, then the universe is not indifferent, it's fertile. It doesn't need a miracle. It needs conditions, patience, and time. That realization changes how we see everything. The fragility of Earth becomes less about loneliness and more about responsibility. The night sky stops being an emptiness and becomes a nursery. And every act of exploration becomes a continuation of the same creative impulse that started 4 billion years ago in a microscopic puddle. Titan, in all its cold strangeness, may never host a single cell, or it may harbor something so alien that we won't recognize it when we see it. Either way, the search itself dignifies us. It tells the universe that the chemistry of curiosity still burns in us, that life is looking back at its own possibility. When you understand what Titan is telling us, you start to hear the same whisper from every corner of the cosmos. Life is not a miracle, it's a tendency. Wherever chemistry can arrange itself into something that stores energy and remembers how, it will. Given the right ingredients, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, nature begins to experiment, and the laboratory is everywhere. Look beyond Saturn. Europa, a moon of Jupiter, hides an ocean twice as vast as all of Earth's seas beneath an icy crust. Enceladus, another of Saturn's moons, vents plumes of salt water and organic molecules through cracks in its surface geysers that Cassini flew through and tasted. Mars, once drenched in rivers and deltas, still carries hydrated minerals and perhaps underground brines. And orbiting distant suns, astronomers have found exoplanets where temperatures, gravity, and atmospheres echo our own. Each of these places hums the same note as Titan, the note of potential. Together, they form a kind of cosmic chord, multiple verses in the same evolutionary song. The more we look, the less exceptional Earth appears. We are discovering that planets with the right conditions are not rare jewels. They are common beads on the string of the galaxy. If the laws of chemistry are universal, then so are the recipes for complexity. Water dissolves and transports. Carbon bonds flexibly. Nitrogen builds scaffolds. Energy flows from gradients. These are not parochial tricks of one small planet. They are the rules of physics written in organic ink. That means that the question, are we alone, may one day feel naive, like asking whether raindrops fall only on our street. Already, scientists can model how amino acids might form in the plumes of Enceladus or the haze of Titan. They can show how ultraviolet light could stitch together sugars on Mars. They can even detect organic fingerprints in the atmospheres of exoplanets hundreds of light years away. Every observation adds another point on the graph of inevitability. Life is not an exception to the universe's behavior. It's a phase of it, matter, learning to manage its own entropy. The Milky Way alone contains roughly 100 billion stars. If even 1 in 10 has planets, that's 10 billion worlds. If 1 in 100 of those sits in a region where liquid can exist, that's 100 million potential crucibles for chemistry. Even if life arises on just 1 in 1,000, the galaxy would still be sprinkled with 100,000 biospheres. Statistically speaking, isolation is the improbable outcome. Connection is the rule. We simply haven't heard the rest of the orchestra yet. So where does that leave us? If life is common, then what makes Earth special isn't that we're alive, it's that we're aware. Consciousness may be the universe's rarest experiment. Matter that not only metabolizes, but reflects. And reflection carries obligation. For the first time in 4.5 billion years, this planet hosts a species capable of understanding its own chemistry well enough to destroy or preserve it. That's the razor's edge of intelligence. The power to recognize the formula of life and to rewrite it. When NASA studies Titan, it isn't just hunting alien microbes. It's refining our understanding of the conditions that sustain meaning. Because every discovery about life elsewhere is also a discovery about how to keep life here. Consider what happens when a society accepts that life might be everywhere. Borders lose a bit of their arrogance. Wars over our resources feel provincial. Environmental neglect begins to look like sacrilege. We start to act not as owners of a rock, but as participants in a continuum that stretches from microbial mats to galaxy. That shift in perspective is more radical than any rocket launch. It's the beginning of a planetary consciousness, a recognition that the line between biology and cosmology is paper thin. The atoms in our blood once rode inside supernovae. The salts in our tears match the salinity of ancient oceans. Every cell in our body carries the memory of chemistry that may also be stirring right now in Titan's hidden sea. We are, in every sense, relatives across light years. Once you accept that life is likely common, a deeper question emerges. How does it stay alive? What strategies does the universe use to keep its sparks burning against the wind of entropy? On Earth, ecosystems achieve it through balance. Coral reefs recycle nutrients. Forests trade carbon for oxygen. Civilizations invent ethics. Perhaps on Titan, balance takes a different form, molecules maintaining equilibrium in the cold. Cycles slower, but no less elegant. If so, then life's essence isn't DNA or protein, it's feedback. It's the loop that keeps a system learning. And if feedback is the secret, then awareness, our kind of awareness, is the universe reaching self-regulation on a conscious level. We are part of that experiment, responsible for whether it succeeds or collapses. From the hydrothermal vents on Earth to the methane lakes of Titan, there's no sharp line dividing alive from not yet. There's only a slope of complexity atoms, to molecules, to metabolism to memory. Somewhere along that slope, physics became autobiography. So when Dragonfly skims Titan's surface and tastes its chemistry, it isn't looking for aliens, it's looking for ourselves, written in another grammar. Every measurement will ask the same quiet question. What was the first sentence the cosmos wrote that meant I exist? Every age of discovery eventually becomes an age of reflection. After every map is drawn, after every ocean is crossed, there comes a moment when the explorers look back at their wake and ask, what have we done with what we've learned? We are living in that moment now. For centuries, knowledge was our lantern against the dark. We learned to split the atom, to edit genes, to turn data into insight. And yet, with each light we ignite, a new shadow appears, the shadow of consequence. When you understand how life works, you inherit the responsibility to keep it working. That's what the search for life on Titan, Europa, and every other world really demands of us: stewardship. Because the universe doesn't hand out meaning, it hands out opportunity. The rest is up to consciousness. Think about it. For 3.8 billion years, life on Earth operated blind, bacteria dividing, forests breathing, oceans balancing carbon without ever asking why. Then, suddenly, one lineage of primates looked up, noticed the stars, and realized that awareness itself had entered the equation. We are that awareness. We are the universe conducting an experiment in moral physics, testing whether intelligence can coexist with survival. Knowing how fragile the biosphere is doesn't doom us. It obliges us. Knowledge is not a trophy on a shelf. It's a lever on the future. And the longer we hold it, the heavier it becomes. When NASA studies Titan, it is not escaping Earth. It is reminding Earth of its own rarity. Because to see another world where rivers run without life is to recognize the miracle of our own, where every drop carries history. To watch methane rain on a dead moon is to understand the privilege of water falling on forests. The more we know, the less excusable our carelessness becomes. We've entered an era where exploration can no longer be innocent. When we send machines to other worlds, we also send our ethics. A drill bit that pierces an untouched ocean carries both curiosity and risk. A satellite that photographs a polar cap carries both data and desire. So the next great frontier of science is not just technological, it's moral. How do we explore without contaminating? How do we search for life without smothering the very possibility of it? How do we turn discovery into empathy instead of entitlement? Every mission briefing should begin with that question. Every scientist should remember that to touch another world is to rewrite its history and our own. In laboratories, a control is the condition we keep constant so we can measure change. In the cosmic laboratory, Earth is the control, the one confirmed instance of life we can compare the others to. If we ruin the control, the whole experiment collapses. That's why climate science and astrobiology are not separate disciplines. They are mirror images. One studies how life survives on this planet. The other studies where it might survive elsewhere. Together they form a single mandate: understand enough to endure. Every glacier that melts, every coral that bleaches is data. Not just data about climate, but data about consciousness, about whether an intelligent species can align its behavior with the equations it understands. The verdict isn't in yet. Look at the spectrum of habitability across the solar system. Mercury scorched, Venus smothered, Mars desiccated, Europa and Titan frozen. Earth, perfectly balanced by accident and by feedback. We live in a razor-thin interval of temperature, pressure, and chemistry. A 2% change in solar output, a few degrees of warming, a few molecules of CO2 too many, and the whole experiment veers off course. To call Earth fine-tuned isn't mysticism, it's measurement. And yet, within that narrow band, life erupted into symphonies of complexity, coral reefs, rainforests, brains capable of wonder. The least we can do is keep the music playing. Preserving this equilibrium is not romantic idealism. It's self-preservation scaled to reality. A civilization that ignores feedback behaves like a planet. Ignoring its climate, it overheats, it collapses, it disappears. Curiosity alone built the rockets and equations that let us touch the stars. But curiosity without conscience is just appetite. What turns curiosity into civilization is empathy, the ability to imagine consequences before they arrive. That's the real lesson of space exploration, foresight. Because the distance between what can be done and what should be done widens with every technological triumph. And that gap is where character is tested. So when we look at Titan and see the chemistry of beginnings, we should also see the ethics of continuation. If life elsewhere proves common, it doesn't diminish ours. It multiplies our duty to protect it. If it proves rare, it makes our obligation sacred. Either way, responsibility wins. Right now, humanity stands at a kind of planetary inflection, point our own event horizon. We can spiral inward, consumed by the gravity of short-term gain, or we can generate enough awareness to escape our self-made orbit. Escape velocity, in this sense, isn't measured in kilometers per second. It's measured in empathy per action, foresight per decision. The laws of physics don't care whether we make it, but consciousness does. And that makes all the difference. If we act as stewards, our story continues. If we act as consumers, it ends as quietly as Titan's methane rain, beautiful, indifferent, forgotten. Maybe the next chapter of progress isn't about speed or profit or colonizing Mars. Maybe it's about learning how to live intelligently within limits, how to see boundaries, not as cages, but as the architecture of sustainability. The universe builds galaxies through balance between expansion and gravity. Why should civilization be any different? To be modern is not to consume faster. It's to understand deeper. To be advanced is not to conquer more territory. It's to extend compassion beyond the species line, beyond the planetary line. That's what awareness demands, the widening circle of concern. Imagine a child born a century from now, looking up at Saturn through some future telescope. She'll see the faint glimmer of Titan and the traces of where our machines once landed. She'll read our data, our code, our equations. What will she think of us? Did we use our knowledge to create or to consume? Did we treat discovery as permission or as purpose? Did we act as if intelligence were a right or responsibility? We can't choose what she discovers, but we can choose the story she inherits. The same chemistry that built Titan's haze built the neurons that are processing these words. The same laws that shape its tides shape our choices. And the same universe that allows matter to become self-aware now waits to see what self-awareness will do. That, in the end, is the responsibility of knowing, to recognize that every equation we solve also solves for us. And that the real experiment, the one the cosmos is watching, is whether understanding can finally evolve into wisdom. Every story of exploration eventually curves back toward home, because the farther we go, the clearer we see what we left behind. When Voyager 1 crossed the edge of the solar system, it turned its camera backward for one last photograph. There, suspended in a beam of scattered sunlight, was Earth a speck less than a pixel wide. Carl Sagan called it a mote of dust suspended in a sunbeam. From that distance, every border ever drawn vanished. Every triumph, every mistake, every civilization, every prayer, every heartbeat existed inside that single dot. That image is still our most accurate portrait. The universe reminding us how small we are and how much that smallness means. We went to Titan to look for chemistry, and we found perspective. We discovered that oceans can exist in darkness, that rain can fall as methane, that the conditions for life are more versatile than our imagination. And somewhere in that data, in the numbers, spectra, and images, was a lesson written not in equations, but in humility. If life can arise in such alien seas, then life is not a local accident. It is the universe expressing one of its oldest habits: organization, persistence, creativity. And if awareness has blossomed here on Earth, perhaps awareness itself is how the universe ensures it won't forget what it has made. We have learned to harness 4 lights: fire, electricity, nuclear power, and data. Now we are approaching a 5th, the light of understanding. It burns not in stars or circuits, but in the space between knowledge and compassion. It is what allows us to look at Titan's frozen oceans and feel responsibility instead of conquest. That 5th light asks for stewardship. It reminds us that exploration without empathy is only expansion. That intelligence without kindness is only computation. And that a species that can reach for other worlds must first learn to protect the one that taught it to dream. Someday, long after we are gone, another intelligence may read the relics of our missions, the tracks of rovers, the recordings of our voices, the reflections of our satellites. It may learn that a small, curious species once looked into the void and tried to understand, and maybe, in that act of understanding, we will have justified our brief moment under the Sunday, because the purpose of exploration was never escape. It was recognition, the realization that We are threads in a cosmic fabric so vast that even the darkest patches are woven from the same light. If the oceans of Titan have taught us anything, it is that life can take many forms, but meaning only one: connection. Between molecule and molecule, between mind and mind, between world and world. So let this be our promise that when we go exploring, we carry Earth with us, not as territory, but as memory. That every new horizon we reach will deepen our care for the one that raised us. That every question we ask out there will make us gentler down here. Because the measure of a civilization is not how far it travels, but how wide it can extend its compassion. And if, one quiet evening, you look up at Saturn and glimpse its dim orange moon, remember, beneath that haze, a small machine built by human hands may be listening to the wind of another world, sending home whispers of possibility. And within those whispers is the oldest truth we've ever learned, that we are, and have always been, the universe aware of itself, trying in our brief flash of time to make that awareness worthy of the stars.